Okay. Linear algebra review. Any questions? Which question should I start with?
Number one.
Number
Yeah.
one. Oh, that's always a good start. Okay. So we have a function from R3 to R3 defined by the following. Take a vector x, y, z. It gets sent to the vector x plus 5y plus 2z minus 5x plus 3y minus z and 7z. So first we want to find the matrix with respect to the standard basis. So T of E1 is T of 1, 0, 0, right? That's what the vector E1 is for the standard basis. So when x is 1 and y and z are 0, you get 1 minus 5, 0. T of E2, which is T of the vector 0, 1, 0. When x and z are 0 and y is 1, you get 5, 3, 0. And T of E3, which is the vector 0, 0, 1. When x and y are 0 and z is 1, you get 2 minus 1, 7. So these three vectors are the columns when you write T with respect to the standard basis. The matrix is 1 minus 5, 0, 5, 3, 0, 2 minus 1, 7. So that's the matrix. Now, if we let W be all the vectors in R3 where the z component is 0, what is T of a vector in that subspace? This is a subspace. So when you let x and y be whatever x and y are, we get z equals 0, you get the vector x plus 5y minus 5x plus 3y. And when z is 0, this is 0. So this vector, whatever its first two components are, the third component is 0. So this vector is in W. So we have that T of W is in W for all vectors W in the subspace capital W. So W is invariant. That's the definition of invariant. A subspace is invariant if you take any vector in the subspace, then the linear operator maps it back somewhere into the subspace. Any questions about that? What about if we take the subspace W, which is all vectors whose only non-zero coordinate would be the first coordinate? Or it's better to say all vectors whose second and third coordinates are 0. So if you apply T to such a vector, you get what? When y and z are 0, you get x minus 5x 0. So this is not in W if x is different from 0, this W. Because I take a vector in W, here's the image, the second coordinate is not 0 if x is non-zero, so it's not in W. So this W, in this case, W is not invariant.
Professor,
Yes.
you say because you said the second coordinate is not 0.
Correct.
So that means,
For example, if I take T of the vector 1, 0, 0, I get the vector 1 minus 5, 0.
Mm-hmm.
This is not 0, so it's not in the subspace.
Okay. So that means W is not variant.
Means it's not invariant, yes.
Okay, cool. Thank you.
Sure. All right. Your next favorite question?
Professor, can we do
Number two.
numbers? Oh, I'm sorry.
It's all right.
Just want to know, Professor, if we could do number 6.
Number 6, okay. So problem 6, we have the following vectors in R2. V is -3, 4. W is 5, 12. And U is -7, 0. And the inner product, so in R2, if you take V is, let's say, x1, x2, and W is y1, y2, the inner product of V and W is defined to be x1, y1, product of the first coordinates, plus the product of the second coordinates. So that's the definition of this inner product in R2. So for these two vectors, the inner product of V and W is -3 times 5 plus 4 times 12. So that's -15 plus 48, or 33. And V and U is the inner product of V and U. That's -3 times -7 plus 4 times 0 is 21. And W and U is the inner product of these two vectors. So it's 5 times -7 plus 12 times 0 is -35. So those are the three inner products. The length of a vector is the inner product of the vector with itself, square root of that. So if you have V is x1, x2, the length of V, when you take the inner product of V with itself, it's x1 squared plus x2 squared. So it's the square root of x1 squared plus x2 squared. Just what you learned in high school algebra or geometry. So the length of the vector V is the square root of -3 squared plus 4 squared, which is 5. The length of the vector W is the square root of 5 squared plus 12 squared, which is 13. The length of the vector U is the square root of 49, which is 7. So those are the lengths of the vectors. And for the corresponding unit vectors, you take V divided by its length. So that's 1/5, or maybe I should write this if you like. It's the scalar 1 over the length of V. You only can do this if it's not the zero vector, because you can't divide by 0. 1 over the length of V times V. That's 1/5 times the vector -3, 4, which is -3/5, 4/5. The length of W, what is the length of W? 13. So that's the vector 5 over 13, 12 over 13. The length of U is 1/7 times the vector -7, 0. So that's -1, 0. That's the calculation. Any questions about that? Okay. Next question.
Number 2, Professor.
What?
Number 2.
Number 2.
Yes. Thank you.
Okay. Number 2, we have a map from R4 to R4 given by T of the vector x1, x2, x3, x4 equals, so these are its 4 coordinates, x1 minus 7, x2, x1 plus x2, 5x3 minus 2x4, minus x3 plus 2x4. So if you want the matrix with respect to the standard basis, T of E1, which is T of 1, 0, 0, 0, when x1 is 1 and the other coordinates are 0, you get 1, 1, 0, 0. T of E2, which is T of 0, 1, 0, 0, x2 is 0, x2 is 1, the other coordinates are 0, you get minus 7, 1, 0, 0. T of E3 is T of 0, 0, 1, 0. So with x1, x2, and x4 are 0, you get 0, 0, 5 minus 1. And T of E4, which is T of 0, 0, 0, 1, you get 0, 0, minus 2, 2. So the matrix for T with respect to the standard basis is 1, 1, 0, 0, minus 7, 1, 0, 0, 0, 0, 5 minus 1, and 0, 0, minus 2, 2. Kind of a block that looks like that. That's the matrix. And if you take a vector x1, x2, 0, 0 in this subspace that I call W1, where the third and fourth coordinates are 0, T of x1, x2, 0, 0, well, when you calculate this, you get x1 minus 7x2, x1 plus x2, x3 and x4 are 0, 0, 0. So this is in W1. So if you take a vector whose third and fourth coordinates are 0, T of that vector gives you another vector with the third and fourth coordinates 0. So it's the image is in the subspace W1. In the same way, you take 0, 0, x3, x4 in W2, T of 0, 0, x3, x4, when x1 and x2 are 0, the first two coordinates again are 0. This is 5x3 minus 2x4 minus x3 plus 2x4. And this stays in the subspace W2. The first two coordinates are still 0. So that's problem 2.
Professor, can you do number 9?
Number 9.
Professor,
Yeah,
is that one? That one is invariant, right?
so W1 is invariant and W2 is invariant.
Okay, thank you.
So in problem 9, we have the vector V, which is 2 minus 7, and the vector W, which is 5, 6. So we were going to sketch these vectors. 2 the 2 minus 7 would be around there. This would be B for 2 minus 7. And 5, 6 would be somewhere up here. So this is the vector V, and this is the vector W. So if you want the component of V perpendicular to W, the component of V perpendicular to W, you take the inner product of V and W, divided by the inner product of W with itself times W. So what is that? The inner product of V and W is 10. Let me just write it out. The inner product of V and W is 2 times 5 plus minus 7 times 6. 10 minus 42 is minus 32. The inner product of W with itself is 5 times 5 plus 6 times 6. That's 25 and 36, which I think is 61. So this is equal to minus 32 over 61 W, or if you like, it's the vector 5 times 32, that's minus 160 over 61, and 6 times minus 32, 6 2s are 12, that's minus 192 over 61. So this is the parallel component of V with respect to W, and the perpendicular component is V minus this parallel component. So that's 2 minus 7 minus 160 over 61 minus 192 over 61. So this is equal to what? This is 2 is the same as 122 over 61. And minus 7 is the same as minus 427 over 61. Minus 160 over 61. Minus 160. So minus times minus is plus. So if I can add correctly, if I haven't made too many mistakes in my arithmetic, this is 282 over 61. And this is minus 427. Oops, sorry, this is plus 192. So 427 minus 192 is I think 235. So this is the V perp. And let's see, if I want to know roughly what this is, that's being lazy. And so 160 over 61, this is sorry, that's not right. 160 over 61 is approximately minus 2.6, and 192 divided by 61 is about 3.1, minus 3.1. So that's the parallel component. 282 divided by 61 is a little bit more than, closer to 5 than 4. 260. 282 divided by 61.
How did you get 61? I'm sorry, it's a little bit hard to see.
How do I get 61? So So here are my vectors v and w. So the component of v parallel to w is going to be some scalar multiple of w, because it has to be parallel to w. And this is the scalar multiple. It's the inner product of v and w divided by the inner product of w with itself. So the inner product of w with itself is 5 times 5 plus 6 times 6. That's 25 plus 36, which is
Professor.
61.
Is that 6.6 or 5.5 plus 6.6?
No, not this is, you're taking the inner product of two vectors. It's 5 times 5, 6 times 6.
Okay, cool. Thank you.
All right, thank you. That was where I was like a little confused because it was hard to tell those numbers right there.
Right. So they're just the numbers from the exercise sheet. Anyway, 282 over 61 is about 4.6, and 235 divided by 61 should be a little bit less than 4, so that's about minus 3.9, let's say. So in any case, this is the parallel and this is the perpendicular component. Let me just try and sketch them. So this is my W, and minus 2.6 minus 3.1 should be right about here. It has to be on this ray going through this line. So this is the parallel component of V, and 4.6 minus 3.9, the 4.6 is around there. It's about here. So this is the perpendicular component. And if you add this plus this, you should get your V. Right? So here's my vector V. This is the component parallel to W, and this is the component perpendicular to W. Let me just check. I take V parallel plus V perp. That's minus 160, 61, not a fraction, over 61, minus 192 over 61, it's that vector, plus V perp, which is 282 over 61, minus 235 over 61. When I add, I get 122 over 61 and minus 427 over 61, which is exactly 2 minus 7. So, which is V. So here's my vector W. I take a vector V. This is my V. I decompose it into it's a piece parallel to W and a piece perpendicular to W. That's the story.
Can you do number 11?
Number 11?
Yeah.
Sure. So in number 11, we start with two vectors, 3 minus 2 and 1, 5. And we want to use the Graham-Schmidt process to construct an orthonormal basis. So let's say I let V1 be the vector 3 minus 2 and V2 be the vector 1, 5. So step 1, I'll keep V1 the same. W1 is going to be V1. And W2 is going to be the component of V2 perpendicular to the vector V1 or W1, which are the same. And so W2 is going to be V2 perp, this perpendicular component. So to get the perpendicular component of W2, it's V2 minus the parallel component. So I take V2 V1 inner product over V1 V1 times V1. So this is V2, and this is the parallel component that I'm subtracting off. And so I have to do this calculation, of course. So V2 is 1, 5 minus some scalar multiple of V1, some scalar multiple of the vector 3 minus 2. And what I'm subtracting off is the inner product of these two vectors. So V1, V2, the inner product is 3 minus 10 or minus 7. So this is minus 7 over the inner product of V1 with itself, which is 3 times 3 plus minus 4 times 4, which is 13. So this is the vector 1, 5 minus times minus is plus 7 over 13 times the vector 3 minus 2. So that's 1, 5 minus. So I have this vector, and I'm multiplying it by the scalar 7 over 13. So I get 21 over 13 minus 14 over 13. If I write 1, 5, if I write these as fractions with denominator 13, 1 is 13 over 13, and 5 is 65 over 13. This makes it easier to subtract. So I get minus 13 minus 21 is 8 over 13, and 65 plus 14, minus times minus is plus, is 79 over 13. So this is a vector W2, and so W1, W2, this is a orthogonal, not yet orthonormal, but this is an orthogonal basis for R2. I have the vector 3 minus 2, and I started with the vector 1, 5, but the perpendicular component of 1, 5 with respect to 3 minus 2 is minus 18 over 13, 79 over 13. So this is a little bit more than 6, and this is a little bit more than a minus a half. So
For questions like this, we should do the little graph and like draw it out too, or
well, I do it.
won't affect us for the test.
If the problem says you only can draw a graph in 2 dimensions. So if the problem says draw the graph, then you should draw the graph. If it doesn't say draw the graph, you don't have to. I like drawing pictures, but you don't have to. It's not part of the problem.
Okay.
So this vector here, so this is my V2, this is my W2, this is the perpendicular component. And then to get the orthonormal basis, I want to let E1 say be W1 divided by the length of W1. So the length of W1, or the length of V1, it was the same, is the length of this vector. 1 over the square root of 13 times 3 minus 2. So that's 3 over root 13 minus 2 over root 13. So these two, W1 and this vector are parallel, but this has unit length. And E2, which I'm not going to calculate because the numbers are just too much arithmetic for right now. You just take the length of this vector, so it's 1 over the length. So the length is the square root of 8 over 13 squared plus 79 over 13 squared, whatever that turns out to be, times the vector. I mean, you can actually simplify this and get the numbers, but it's not necessary. That's problem 11.
Thank you.
Let's see, I should do an eigenvalue problem because they're very important. So one where you have to calculate the spectrum. Maybe I'll just start with number, I'll do number 4. So number 4, I have the matrix, and we call it A, which is 1, 2, 2, 3. And I want to find the eigenvalues and eigenvectors. So I want to find lambda, that's an eigenvalue, such that for some vector xy, A applied to xy is lambda xy. For xy, not the 0 vector. So A applied to the vector xy, that's 1, 2, 2, 3 applied to xy, you get the vector x plus 2y, 2x plus 3y. And we want to know, can you find xy and lambda such that this is lambda times the vector xy, which is lambda x times lambda y. So we have to solve some equations. X plus 2y equals lambda x. 2x plus 3y equals lambda y. This is the same as saying, I put everything over on one side, lambda x minus x, lambda minus 1x, minus 2y equals 0, and minus 2x plus lambda minus 3y equals 0. So I want to be able to know for what lambda can I solve these equations. It's just 2 equations and 2 unknowns. And so for what lambda does a solution xy not equal to 0, 0 exist? And 2 linear equations and 2 unknowns have a non-zero solution. So this is high school algebra. You have ax plus by equals 0 and cx plus dy equals 0. This has a non-zero solution that is not both x and y are 0 if and only if AD minus BC is 0. So this is A, B, C, D. So you have a non-zero solution for lambda if AD, lambda minus 1, lambda minus 3, minus BC, minus 2 times minus 2 is 0. This says lambda squared minus 4 lambda plus 3 minus is minus 4 equals 0. Or lambda squared minus 4 lambda minus 1 is 0. So let's see. And the solutions of this equation are lambda equals 4 plus or minus the square root of b squared minus 4ac over 2. That's 4 plus or minus root 20 over 2. That's equal to 2 plus or minus root 5. So, oops, sorry, that's, I did something wrong, so let me just double check my arithmetic here. 1, 2, 2, 3 is x plus 2y, 2x plus 3y. So x plus 2y equals lambda x. Oh, lambda, yeah, lambda minus 1x minus 2y equals 0. Minus 2x plus lambda minus 3. So I get lambda minus 1. So this determinant, AD minus BC, is lambda minus 1, lambda minus 3, minus 4. This is lambda squared minus 4 lambda plus 3. It's lambda squared minus 4 lambda minus 1. So lambda is minus b plus or minus the square root of b squared plus 4, that's 20. 20 is 4 root 5. Yeah, I get 2 plus or minus root 5. Oh, sorry, that's right. That's exactly what I wrote down as the solution. So these are the two eigenvalues. So we have the eigenvalue. So the spectrum is, the first eigenvalue is 2 plus root 5. And the second eigenvalue is 2 minus root 5. And then we need to compute eigenvectors. So you want to find a vector xy such that axy is 2 plus root 5 xy. That will be an eigenvector for this first eigenvalue. Or this is 1, 2, 2, 3 applied to xy, which is x plus 2y, 2x plus 3y equals 2 plus root 5 x, 2 plus root 5 y. So we want to solve the equations. The first equation is x plus 2y equals 2 plus root 5 x. Or 2y equals, subtract x, 1 plus root 5 x. So y is 1 plus root 5 over 2x. For any x you might want to choose. So, for example, just to get rid of the denominators, if you let x equal 2 and y equals 1 plus root 5, so v1, the vector 2, 1 plus root 5, is an eigenvector for the eigenvalue lambda 1 equal to 2 plus root 5. And you can compute an eigenvector for the second eigenvalue, 1, 2 minus root 5, in a similar way. Questions about this? Let me do another eigenvalue problem, because these are very important in applications of linear algebra everywhere. Economics, physics, any field that you might like.
Professor, that's number 4, right?
Sorry?
The one that I just finished is number 4.
Yeah, this is problem 4.
Okay. Thank you.
Let's do, I don't know, 3b, say. So here I have the matrix B is equal to minus 3, 0, 5, 2. So I want to know when is bxy, which is minus 3, 0, 5, 2 times the vector xy. That's minus 3x plus 5y, 0 plus 2y, equal to some lambda x, lambda y. So I'm a little bit puzzled by something here. So this says minus 3x plus 5y has to equal 0, and 2y has to equal lambda y. So there are two cases, I guess. So this, sorry, this is lambda x. So this first equation is lambda plus 3x minus 5y equals 0, and lambda minus 2y equals 0. So if y is different from 0, then lambda must equal 2 to solve this equation. And if lambda is equal to 2, then this says 5x, that's lambda plus 3x, if lambda is equal to 2, equals 5y, which means x equal y. So we get one eigenvalue is 2, and the eigenvector has to be the vector when x equals y. So for example, if we let lambda 1 be 2.
Professor?
Yes.
Is that lambda equal plus 3y or what? 5x is equal to lambda plus 3y? Equal to 5.
Sorry, I don't see. So here is the vector, here's the matrix B. When you apply that matrix to a vector, you get this vector.
Yeah.
And the question is, for what lambda is this vector equal to lambda x lambda y? Which is the same as solving these two equations. Minus 3x plus 5y is lambda x. This equation is the same as lambda plus 3x minus 5y equals 0. This equation is the same as lambda minus 2 times y equals 0. Now, if you look at these equations, if y is different from 0, then lambda must equal 2. And if lambda equals 2, this says 5x equals 5y or x equals y. So if you take the vector with x equal y, say 1, 1, that should give you, this has to be an eigenvector with eigenvalue 2. And in fact, b of 1, 1, so that's minus 3, 5, 0, 2, applied to 1, 1, is 2, 2, which is 2 times the vector 1, 1. So b of 1, 1 is 2 times 1, 1. That means this is an eigenvector with eigenvalue 2. So there's a mistake in the notes. I had spec v, well, so minus 3. It should be, let's find the other eigenvalue in one. So that's if y is different from 0. If we look for a vector with y equal to 0, then x has to be different from 0. And lambda plus 3 times x equals 0 means lambda has to equal minus 3. So the other eigenvector, other eigenvalue must be -3. And when lambda is -3, x can be anything. Of course, so you have x, any number different from 0 and y equals 0. For example, I could just let x equal to 1. Look at the vector 1, 0. So b applied to the vector 1, 0, -3, 5, 0, 2, applied to 1, 0 is -3, 0, is -3 times 1, 0. So lambda 2 equal to -3 is the second eigenvalue. So the eigenvalues are -3 and 2. So for this matrix, the spectrum, the set of eigenvalues, there's 2 and -3. And I actually constructed the eigenvectors that associated with each of them. Any questions about this?
What about 3C? You done with that?
Okay, let's look at 3C.
Yeah.
So here I have the matrix 1, 0, 1, 1. And if I apply that to a vector xy, I get x plus y. And I want to know, when can I solve the vector equation? X plus y is equal to lambda times xy, which is lambda x, lambda y. So that means x has to equal lambda x, and x plus y has to equal lambda y. Now, if x equals 0, then this equation becomes then y has to be different from 0 if lambda is an eigenvalue. So y equals lambda y implies lambda equals 1. So if x equals 0, lambda has to equal 1. And if lambda equals 1, y can be anything. Lambda is 1, y equals y. So I can take E1 to be the vector x equals 0, y equals 1. Let me just check and see if this works. So c times the vector 0, 1, that's c applied to the vector E1, is 1, 0, 1, 1 applied to 0, 1. That's equal to 0, 1, or 1 times 0, 1. So E1 equal 0, 1 is an eigenvector for the eigenvalue 1. We got that in the case of x equals 0. If x is different from 0, then x equals lambda x again implies lambda equals 1. So lambda equal 1 is the only eigenvector, only eigenvalue. And if lambda equals 1, from these equations, you get x equal x, x plus y equals y, so x has to be equal to 0. So in this case, the set of eigenvectors is just, it's one-dimensional. It's all vectors 0, x, 0, 1. So there's only one eigenvalue, 1, and the corresponding eigenvector is 0, 1. And let me do one more eigenvalue problem, because these are really important. Let's look at number 5. So in number 5, we have a matrix 1, 2, 3, 4. So if A applied to x, y, that's what, 1, 2, 3, 4 times the vector x, y. That's x plus 2y, 3x plus 4y. And if that's equal to lambda times some eigenvector xy, or lambda x, lambda y, we're looking for solutions of the equations x plus 2y equals lambda x, 3x plus 4y equals lambda y. If I move everything over to the right, this is the same as lambda x, lambda minus 1x minus 2y equals 0, minus 3x plus lambda minus 4y equals 0. So I want to know for what lambda is there a non-trivial solution, non-zero solution, x and y, to these two equations. So I look at this determinant, AD minus BC. This is A and this is D. So lambda minus 1 times lambda minus 4 minus BC minus 2 times minus 3. So this is lambda squared minus 5 lambda plus 4 minus 6. So I get the equation lambda squared minus 5 lambda minus 2 equals 0. So this is the characteristic polynomial quadratic equation I have to solve to find the eigenvalues. So if I solve this, I just use the quadratic formula. Lambda is 5 plus or minus the square root of b squared minus 4 AC plus 8 over 2. So this is 33. I get 5 plus or minus the square root of 33 over 2. So my spectrum consists of two eigenvalues. Lambda 1 is 5 plus root 33 over 2. And lambda 2 is 5 minus root 33 over 2. So these are the eigenvalues. And for each eigenvalue, there has to be an eigenvector. So let's look for it. So we have to solve these equations for these two values of lambda. I'll just do it for lambda 1. So if I look at these equations, lambda minus 1, I get, what does this equation say? Lambda minus 1, so that's 3 plus root 33 over 2 times x minus 2 times y equals 0. So that says that 2y is 3 plus root 33 over 2x, or y, for any x, y is 3 plus root 33 over 4, just dividing by 2x. So for example, if I let x equal 4 and y equal to 4 times, just cancels the 4, 3 plus root 33. So this vector called E1, this
Professor,
vector,
can you move it down a little bit? Can't see.
Yeah.
Thank you.
I'm just, so this is just, baby algebra. I'm just solving this equation for y. So y is this times x. So the simplest x I can pick is 4, just to get rid of the fractions. So if I take 4, 3 plus root 33, this vector is an eigenvector for the eigenvalue 5 plus root 33 over 2. And you can find the other eigenvector in the same way. Let's look at problem 13. So here the vector space is R2, and I take the vector 1, 1. And so I just have a set with one vector in it, 1, 1. And the perpendicular or orthogonal component of x is all the vectors v in R2, v equal to xy, where the inner product of these two, let me call this something, I'll call this x. Call this w. So it's all vectors v, where the inner product of v and w is 0. All vectors perpendicular to this vector w. So this is all vectors x, y, where the inner product of x and y and 1 and 1 is 0, but this inner product is x plus y. So it's all vectors where x plus y equals 0. This is all vectors x, y in R2, x plus y equals 0, which is the same as y equals minus x. This is all vectors of the form x minus x, which is exactly the set of all scalar multiples. This is x times the vector 1 minus 1. So this is, so x perp is the one-dimensional subspace spanned by the vector 1 minus 1. And if you draw a picture of this, you can see exactly why this is. Here is the vector 1, 1. The vector 1 minus 1 is here. And all scalar multiples of that are just all the points on this line. So this is all vectors in the plane perpendicular to this. So this one-dimensional subspace, this is my x-perp. Here's a vector, and all the vectors perpendicular to this lie on this line through the origin. This is part A. Any questions about this? This is very nice geometry. Let's look at 13b.
So Professor, for A, it was y equals negative x for the computation.
So if y is minus x,
Mhm.
then your vector is x minus x, which is just x times the vector 1 minus 1. So it's
Okay.
all scalar multiples of 1 minus 1.
Okay, thank you.
Problem 13b, we take x to be the set consisting of just the single vector 2, 3. You can actually draw a picture of what the answer is going to look like before we even start. Here's the vector 2, 3. What are the vectors perpendicular to that? There's every vector that looks like this. Every vector on this line is perpendicular to 2, 3. Let's see, how do we find that algebraically? So x, y, and 2, 3, the inner product is 0. If and only if, what's the inner product? 2x plus 3y equals 0. So y is minus 2/3 x. So xy is x minus 2/3 x. Or I can write this if I want to avoid fractions. Xy is anything of the form minus 2x over 3, 3x over 3, like that. It's like x over 3 times 3 minus 2.
Yeah, we can see that. Thank you.
So x-perp is all scalar multiples of the vector 3 minus 2. Here's 3 minus 2. Here's 2, 3. So here's my vector that I started with, and that's, and everything perpendicular to it is on this line.
Professor, can you do number 14?
Yes.
All right, thank you.
So for 14, that's a nice exercise in using an orthonormal basis. So suppose we have W is a subspace of Rn of dimension K. So if we take any basis with W, if we use the Graham-Schmidt orthonormalization process, there exists an orthonormal basis, E1 up to EK for W. So here we have V, and sitting inside V we have W. We can extend E1 up to EK to an orthonormal basis, E1 up to EK, EK plus 1 up to EN. We have an orthonormal basis for the whole vector space. Now, so W in W means you can write W as some summation, let's say xi ei, I goes from 1 up to k. Because if you're in the vector subspace W, the vectors is k dimensional, and these k vectors form a basis. If V is any vector in V, you can write V as some linear combination yi ei. I goes from 1 up to n. Because E1 up to En is a basis for all of V. And the inner product of W and V is 0 if and only if, see, what's the inner product of W and V? It's summation xi yi, I goes from 1 up to k. When you take the inner product of these coordinates and these coordinates, this is what you get. So this has to equal 0. Maybe a nicer way to see this is, if V is in W perp, then the inner product of V with EI is 0 for all I from 1 up to k. Because E1 up to EK are in W, and the vector V has to be perpendicular to all of these. But the inner product of V and EI is Y sub I. So Y sub I equals 0 for I going from 1 up to k, which means V is some linear combination of just the vectors from k plus 1 up to n. These are n minus k vectors. So any vector in V perpendicular to W must be a linear combination of these n minus k vectors. And any linear combination of these n minus k vectors is perpendicular to everything in W. So the orthogonal complement of W is the n minus k dimensional space spanned by the vectors ek plus 1 up to en, and they're exactly n minus k of them. That's the story. Questions about this? Or anything else?
Professor, can you do number 12?
Yeah, just a
Thank you.
lot of calculation. So for number 12, we have the vectors 1, 2, 3, 2, 3, 1, 3, 1, 2. So if you want to prove it's a basis, let's see, hope it is. Suppose that some linear combination of these vectors is 0. X times 1, 2, 3 plus y times 2, 3, 1 plus z times 3, 1, 2. So this is equivalent to x plus 2y plus 3z, 2x plus 3y plus 1z, 3x plus 1y plus 2z equals 0, 0, 0. So you have to see if this set of 3 equations and 3 unknowns has a non-zero solution. So x plus 2y plus 3z equals 0. 2x plus 3y plus z equals 0. 3x plus y plus z equals 0. Suppose we try to solve these equations. So let's say I want to eliminate x. So I can take the second equation minus 2 times the first equation. So I get 2x minus 2x, 3y minus 4y, z minus 6z equals 0. If I take the third equation minus 3 times the first, 3x minus 3x is 0. 1 minus 6 is minus 5. 1 minus 9 is minus 8. So this says minus 5y equals minus 8z. So 8z equals minus 5y minus y. So this is 5 times minus y. Minus y is 5z. So 8z has to equal 25z. So z has to equal 0. So if z is 0, then for example, 2x plus 2y equals 0, 2x plus 3y equals 0. If I multiply this equation by 2 and subtract, I get and y equals 0, and then x equals 0. So if I just do my sort of high school algebra, I have 3 equations and 3 unknowns. I try to solve them, and I find the only solution is x equals y equals z equals 0. So these 3 vectors I've started with are linearly independent, so they do form a basis. Right? There are lots of ways to do this, but this is a simple way. Okay. So then we apply Gram-Schmidt. So I have my vector v1, which is 1, 2, 3. And then I have my vector v2, which is 2, 3, 1. So I'm going to let W1 be V1 and W2 be V2 minus the component. So I want V2, I want W2 to be the component of V2 perpendicular to V1 or W1. So what is W2 going to be? It's going to be V2 minus the inner product of V2 and W1 divided by W1 inner product of W1 times W1. This is the component of V2 perpendicular to W1. So V2 is 2, 3, 1 minus the inner product of these two vectors is 2 plus 6. 2 plus 6 is 8, plus 3 is 11 over the length of V1 or W1. So the sum of the squares of the components, 1 plus 4 plus 3 is 14 times 1, 2, 3. So W2 is 2, 3, 1 minus 11 over 14, 22 over 14, 33 over 14. So 2 minus 11 over 14, 28, that's 17 over 14. 42 minus 22 is 20 over 14. 14 minus 33 is minus 19 over 14. So this is my vector W2. And then to find W3, I take the vector V3, which is 3, 1, 2, minus the component of V3 perpendicular to W1 and minus the component of V3 perpendicular to W2. So V3, that's the vector 3, 1, 2. What's the component of V3 perpendicular to W1? That's V3 minus the inner product of V3 and W1. Let me just write it down. Times W1 minus the component of V3 perpendicular to W2 so you have to do all the, so now that's the formula. And now you just have to do the calculations, which take a bit of time and work. But you just plug in the numbers and the answers will come out. Oh, and then when you have W1, W2, and W3, that's an orthogonal basis. And you get unit vectors by dividing each of those vectors by its length. And now you have an orthonormal basis. And you're done. So let me remind you that I have office hours in a little while today. I think maybe 1:30, I'm not sure. And this evening, and again tomorrow, and also tomorrow night. So there's plenty of time to log on if you have some additional questions before the exam, which is 11 o'clock on Wednesday. Questions?
That's gonna be the earliest we can start the test is at 11 o'clock.
Yeah. Class,
What time does the test finish? Same as last time?
yeah, it's a, yeah, 2 hours, 11 to 1.
I get my extended time for it though, right?
Yes.
Okay.
And Professor, I have a question. After this test, when's the final gonna be again?
I will tell you, I mean, the final exam time set by the school, and it is, oh, it's pretty soon actually, because it's almost the first day of final exam period. Final exam is Wednesday, May 18th.
Okay. And Professor, everything on the what's it? I remember you saying that like if you wanted to add like more stuff like on the test, like you'd update the review. Or is the review and the test like going to be the same questions, or like
Well,
have
the
you just-
same types of questions,
or the
yes.
same? Yeah. Just want to make sure.
Yeah, yeah. I mean, there are a couple of topics that I did not put on the review sheet because I want to spend some more time going over them, like change of basis.
Okay.
But that is not on the, that'll be on the final exam, but it's definitely not on this week's exam.
Okay. Thank you.
And if we do well on this week's exam and the final, even if we did terrible on the first test, there's still a chance of us passing with a decent grade.
Oh, absolutely, yes. Yeah, no,
Okay.
if you do barely on the first exam, but you sort of catch up and do okay, then I'll pay less attention to the first exam.
Oh, all right. Because I've been freaking out about that ever since, even though you said that it was fine, I've just been like, oh no, I'm gonna fail.
Well, hope not. Right?
Yeah, I hope not either.
Yeah.
Because I was hoping that if I get at least like, 85 on this and like 85 on the final, I'd pass with at least maybe a B, even though I got like a 16 on the first test.
If you can get like a B plus on this exam in the final, I'll give you a B. I give anyone a B. Yes.
Cool. Thank you.
But I do look at the total grades for the semester, but then I look and see whether, if you did badly in the beginning, but you caught up, then that's fine because you learned the stuff in the end.
Mm-hmm.
Okay. Yeah, every lecture is uploaded to YouTube. So this will be uploaded in half an hour or so. All right, all. Come to an office hour if you have questions. See you otherwise on Wednesday. Bye.
All right. Take it easy, Professor.